continuing now with number 6. So we've been given these logic propositions. We have to write in words P and then the OR with the line underneath it and then the Q. So Sean is at school, or Sean is playing a game on his computer, but not both, thanks to that line underneath the OR. Write in words the converse of P implies not Q. Well, the converse, we're simply going to switch the direction, meaning that the P and the not Q are going to be in reverse order. So that would be not Q implies P. So let's put that into words. Okay. So Sean, if Sean is not playing a game on his computer, then it's pointing to P. Then Sean is at school. Alright, let's complete the truth table. So we've got not Q, that's the opposite. And then we've got P pointing to not Q. P pointing to not Q. This right here is a false. Everything else will be true. Let's move on to number 7. So we have to write this compound proposition in words. So the number is even and the number does not end in 0. I'm not really sure what just happened there. Let's go back and see if I can undo that. Alright. Wow, weird. The number is even and the number does not end in 0. And I have to stick an if now in front of this because I've got this arrow and it's pointing to, so then not P, the number is not a multiple of 5. Okay, let's consider the statement. If the number is a multiple of 5 and it is not even, then it will not end in 0. Write the statement in symbolic form. So if means that we're going to have an arrow in the middle. Let's write the antecedent, the part first. The number is a multiple of 5. There we go. Oops, I need to leave a little bit more space because I've got an and coming in next. So P, and is not even, and not Q. I'm going to stick this into parentheses to show that these are the two things that together are forming my argument. These are all of the, what do you call them? Propositions, and then it's the conclusion that we draw from these. Then it will not end in 0. Now we need to write the contrapositive of this statement. The contrapositive not only switches the order of the two sides of the implication, it also turns them both into nots. So in symbolic form, the not R will move to the left and become the negation of that, which is simply R, and that's pointing to the negation of the left-hand side. And I suppose if you wanted to use De Morgan's law, you could distribute this negation to the P and also to the Q, which would just make it a positive Q. Either one would be fine. Right, number 8. We're on to the probability questions. Got a fair 6-sided die, which you can see has been represented with the numbers 1, 2, 3, 4, 5, and 6, and that's why we're making a 2-dimensional grid, a fair 4-sided die with the 4 numbers 1, 2, 3, and 4. These two dice are now rolled. The following diagram shows the outcomes. Clearly there's 24 different outcomes. Find the probability that the two dice show the same number. So we could have a 1 and a 1, we could have a 2 and a 2, a 3 and a 3, a 4 and a 4. So there's going to be 4 ways out of 24, which simplifies to 1 over 6. You could express that as a decimal or as a percent, but why bother? IB is fine with fractions if it hasn't specified how you should leave your answer. If you do round to a decimal or a percent, don't forget to round to 3 significant figures or more. Find the probability that the difference between the two numbers shown on the dice is 1. So the difference between the two numbers must be 1. Let's indicate these ones now. I'll use a different color so that we can not get confused with what I've already been doing. So if the numbers are going to be different by 1, that could be, say, 1 and a 2. Because 1 and 2 are different by 1, aren't they? So that would be, say, a 1 on this dice and a 2 on this dice. Or maybe it means a 1 on this dice and a 2 on this dice. So there's those two possibilities. Another way that two numbers could be different by 1 would be 2 and 3. So here's a 2 and a 3 in that order, and a 2 and a 3 in the other order. And a 3 and a 4 follows the same pattern. And we end up then with 6 spots out of 24. And so our answer would be 1/4 when I reduce the fraction. And as always, yes, you could express it as a percent if you wanted. Find the probability that the number shown on the 4-sided die is greater than the number shown on the 6-sided die. Given that the difference between the two numbers is 1. Alright, now given that the difference between the two numbers is 1, this is a key phrase because this shows us what the given condition is. So we have given you that we're only going to be looking at the 6 possibilities that we just saw a moment ago where the difference between the two numbers was 1. We're reducing our sample space to only these 6 cases. I've given you that we are in one of these 6 situations. So our denominator now is just 6. In how many of these cases then, I've given you the difference between the two numbers is 1, so in how many of those 6 cases is the number on the 4-sided die greater than the number on the 6-sided die? Let's have a look. Well, here's one such case. The number on the 4-sided die is 4. That's greater than the number on the 6-sided die. So that's one case. And here's another one, and here's another one. But these 3 cases, it's the number on the 6-sided die which is greater than the corresponding number on the 4-sided die. So clearly there are 3 of our 6 possibilities, and 3 over 6 naturally reduces to 1 over 2. Another way you could have solved this problem would have been by using the probability formula that says that conditional probabilities. So we're saying find the probability that the number shown on the 4-sided die is greater. So I'm going to notate it like this. The 4-sided die is greater than the 6-sided die. Given that the difference between the two die difference is equal to 1. So I'd notate it like this. So according to the probability formula, that's going to be equal to the probability of both of these events happening at the same time divided by the probability of the given event occurring. Well, the probability of the 4-sided dice being greater than the 6-sided dice and at the same time the difference being 1 is 1, 2, 3 out of 24. So 3 out of 24. And we're dividing this by the probability that the difference between them is 1. We already had that it was 6 over 24. And you'll see that the 24's cancel. And we have again 3 over 6, which reduces to 1 over 2. Number 9. When Andy plays tennis, 65% of his first serves go into the correct area of the court. You can see this, 65 or 0.65. I'm glad that they're drawing the tree diagram with decimals, because drawing it with percentages is almost certain death. If the first serve goes into the correct area, his chance of winning the point is 90%. So if his first serve goes in, then his chance of winning is 0.9. So you see, basically you were given at this stage that the first serve went into the correct area, so we can walk along the path to here. We now know that we are here, the first serve is in. Then his chance of winning the point is 90%, and so that's the given, the conditional probability. Given this, then this is the case. Let's continue. If his first serve does not go into the correct area, which is down here, first serve is out, then Andy is allowed a second serve. And of these, 80% go into the correct area. There's the 80% where the second serve is now in. If the second serve goes into the correct area, so we are now here, second serve is in, his chance of winning the point is 60%. There it is, 0.6, which of course means 0.4, 40% losing. But if neither serve goes into the correct area, then Andy loses the point. This is known as a double fault. And so he automatically loses, and this will happen with a 100% certainty. If he misses both serves, he loses the point. It's over. He lost the point, 100%. Find the probability that Andy loses the point. Well, there are three paths here in which Andy can lose the point. There's this one where he got the first serve in but then lost the point. There's this one where he got the second serve in but then lost the point. And then there's this one where he actually didn't get either serve in at all. Let's calculate these three probabilities and then add them together to find the total probability of Andy losing the point. This first one then will multiply the probabilities along the path. 0.65 times 0.1 gives us 0.065. Second probability, 0.35 times 0.8 times 0.4. I have to do that one on the calculator, I'm afraid. 0.35 times 0.8 times 0.4. And that gives me 0.112. And then the last one, 0.35 times 0.2 times 1. Well, thankfully multiplying by 1 doesn't change anything. I can do this. 0.35 times 0.2, that gives me 0.07. Okay? Or 070 if I like. And if I add these three probabilities together, plus 0.065 plus 0.112. Oops, I already had that one, darn. 0.07. There we go. I get a total probability of 247. 24.7% chance of him losing the point. Number 10. We got two probabilities, A and B. If events A and B are mutually exclusive, remember mutually exclusive means that these events do not overlap at all. So that means that the probability of both of them happening at the same time, probability of both events would have to be equal to 0. They can't both happen at the same time. There is no region belonging to both. Now let's suppose events A and B are independent. As soon as you've been given, because you've been given that they are independent, well then we know that the probability of A and B is equal to the product of their probabilities. Anytime you know that they are independent, you are allowed to multiply them as given. So 4/13 times 5/13 gives us 20 over 169. And part C, let's suppose that you've been given the OR. If you know the OR, well then we should use the formula, the golden rule, that says that the OR is equal to the sum of the individual probabilities, but minus the possibility of them both being included, so that we don't count this region twice. And so let's substitute now. 7/13 is equal to 4/13 plus 5/13 minus the value that I'm trying to find. You could call it x if you don't want to keep writing it out in full. I'm going to bring this value to the left-hand side where it becomes a positive. And 4 plus 5, that's 9/13. And I'll bring this 7/13 over to the right-hand side where it becomes negative. And I discover that my probability of both happening is 2 over 13. Alright, we'll do the last 4 problems in the final video.